We weren't here for the residents on Saturday. Yes. So I gave a presentation very similar to this to residents. So my apologies to those who heard it before, but this is slightly different, a bit more focus of on the occultation side. Now, I hope everyone's heard of the DART mission, but I've got a little bit about it. But first of all, astrometry from occultations. Traditional astrometry, you're an observer on the surface of the Earth. You look up there to the skies and you see some stars. You sort of think you know where they are, but the star images, whilst you know the position of the star highly accurately, but it's a blurred image, and you've got an image with an asteroid on it, and you measure the location of the asteroid relative to those images. And there's all sorts of assumptions and approximations built into the process, and you report a position. Occultation observations are fundamentally different. Instead of looking at a position up here, the reported position is down here. Now, just to explain this, for all the analysis work, and it's actually on predictions as well, we imagine that there's a plane through the center of the Earth which is normal to the direction to the star up there. And you predict where the star and the asteroid is, and the prediction fundamentally puts a shadow on the fundamental plane, and the prediction generates the position of the shadow on that fundamental plane, and you transfer it onto the surface of the Earth. In the measurement stage, we measure the location of the shadow, make the observations on the surface of the Earth, but that's all projected onto this fundamental plane. And this makes a fundamental difference on how we report the observation. If you're an observer on the Earth surface, you report right ascension and declination. For our occultation observations, we report the location of this point, which is inside the Earth. There's X, Y, Z coordinates, which are highly precise, and the actual numeric precision of what we report is at the 1 meter level. Quite a precise reporting mechanism. The important thing is here is that the position of the star is very well known. We've used the full accuracy of Gaia, and the shadow is very well defined, you hope, and you have a position here which you measure notionally to 1 meter accuracy. So you finish up having a very accurate measurement, which is fundamentally much more accurate than doing optical measurements. The process of reduction includes all sorts of corrections. We take into account the variability of the Earth's rotation. The extreme one is you're on the surface of the Earth, you record a time. Very important you get the time correctly. But we do all the analysis on this plane here, and it takes time for the light to travel through the Earth to get down to here. All the observation event times have a very small correction applied, so it gives you the time on this fundamental plane. Now, move on to the next one. This is just a simple comparison of the reporting mechanism. If you're doing optical measurements from the traditional CCD, you have a station number identification, which gives you latitude, longitude of where you were. You have an observing time. and you report right ascension and declination, and you'll have reported uncertainty in right ascension and declination. You can see here points for this particular observation, 0.37 seconds and 0.47 seconds uncertainties in RA and DEC. The occultation observation, it's a fixed MPC code 275, which is for the center of the Earth with this type of observation. And these are the XYZ coordinates of that location. That's what we report, not right ascension and declination, but those coordinates are there. And we also report the right ascension and declination of the star, because that is the position of the asteroid as seen from that location. And the important thing, when you do all the analysis and you look at what the residuals were, or the uncertainties were with that position, 0.0014 arc seconds and 0.0012. 0.0014 compared to 0.37, that's a factor of 200 smaller. We have very high astrometric precision. Now, a bit about DART. DART was about testing the possibility of deflecting an asteroid if it was heading towards the Earth. And it's a deflection that you would have to apply some years in advance. It's not something you can do if the thing is going to hit the Earth next week. But if it's going to hit us in 5 or 10 years' time, it's a very viable method. The target was a satellite of an asteroid. The main asteroid, that's the size of it in meters, and the target 160 by 120 meters. Think of something about the size of the Melbourne cricket ground, but a ball size, that size. Made of rock or something. And the primary objective was to change the orbit of Dimorphos around Didymus. Actually, I'll show it on the next slide. Here's a picture of this situation. There's Didymus and Dimorphos. Dimorphos has an orbit around there. Dimorphos in the orbit was coming in this direction, the orange arrow. Sorry, the green arrow is where Dimorphos was coming. The DART object, the DART thing, was coming in this direction, and stuff was thrown out from Dimorphos in that direction. The primary purpose of, or measurement thing of the impact was Dimorphos coming this way, bashing in that direction. It slowed the orbit, the asteroid down, put it into a slower or lower orbit with a shortened orbital period. And the orbit was reduced in period by 5%, a significant change in the orbital period. And they were able to measure that quite accurately, looking at mutual eclipses and occultations. And an interesting thing about the impact is has an impact and it throws up a whole heap of material, which we saw in the images, the plume of material coming out. And that came out in that direction. Now, the mechanics of this is you have the projectile coming in and imparts angular momentum. And then you have the ejector coming out this way, which has its own momentum. If that ejector comes out here, but stays within the gravitational boundaries, then that has no effect on it. But if that ejector leaves the system, it has the effect of increasing the momentum that's added to the asteroid, the body. Stuff thrown out this direction is carrying momentum. If it's lost to the system, then the effect of that thing is actually an equivalent amount of momentum is transferred in that direction. And they have a factor called beta for this. And it's an important factor because if you're trying to change the motion of the body, it's not just the momentum from the projectile that changes its orbit, it's also the effect of the material ejected from it, and it enhances the amount of momentum that's transferred. And it's not a trivial amount. We'll come to that in a minute. Now, IOTA's involvement in this, we were asked to try to get accurate astrometry from it, tied up with a European Space Agency probe, which was launched late last year. The spacecraft is going to fly by Didymus, and the aim of that is to see what the effect of the impact was in terms of changes and so forth, and of course have a probe up there which can look at detail the whole system and get the position of it as well. And they wanted to make sure they knew where to send the probe to. So getting accurate astrometry was important. The reason for this, and I'll go back, I hope. Oops. Oh, how do I go back?
The cursor on the left-hand side and then click.
That's
Previous.
Previous.
Again.
Previous. Now I want to go to previous. All the probe hit Dimorphos. The Dimorphos is bound to Didymus. So the change of momentum on this has an effect on the whole system. So even though we hit the probe hit that, the motion of the whole system is affected by that impact. And that was a secondary component of what was getting out of this impact. The initial thing was, how much did you change the orbit of Dimorphos around Didymus? The secondary issue, and it is very much a secondary issue, is how much does that change the orbit of Didymus around the Sun? And that's where the occultation stuff has turned out to be somewhat exciting. We had that request was followed up enthusiastically by people in IOTA. We had successful observations in US, Japan, and Europe, and Australia. All our regions had success. European Space Agency, apparently they thought the occultation stuff, well, they don't know what they're doing or whatever. They didn't believe the occultation stuff was going to provide anything reliable or useful. We obtained the occultation results, forward those to people at JPL, run the Horizon system. We're in a position that people would make an observation, the observations would come through to me, and within an hour of me getting the observations, the astrometry was going to JPL, and for many instances, the orbit was updated within an hour. It was sort of a significant level of excitement and priorities. And the astrometry is done with the cult. I should note here that several years ago, I spent a period of over 12 months working with the Horizons people to make sure the astrometry generated from occultations was truly rigorous. And originally we used to do an RA and declination reporting, and the horizons people advised me and gave me guidance to actually do the reporting of the centre of the shadow on the fundamental plane. From the orbit analysis side, our observations are 100% equivalent to the astrometry derived from orbiting satellites. Our observations are like an orbiting satellite, with the satellite being inside the Earth. At the start of last year, we got an observation from Peter Skutsky, who was in Melbourne on a work visit. He had brought his telescope, and Peter Skilton and a couple of others down there had a go at doing it. They had problems with cloud. They got a position and they had a go at the orbit, incorporating that. And something's interesting going on here. And that's where the interest really took off. Now, this is just to give you an indication of the nature of the observations we were having to deal with. This was the first occultation detection in October. Here are the light curves. So for those that are concerned about how good their light curves are, I mean, that's a nice light curve there. It's clear as whatever, and there's a fairly nice light curve. But given the importance of it, you've got a light curve, you'll try to get what you can out of it. Here's an image, a plot of, that's Didymus. The shape model is pretty well known, and you can see the uncertainty bars at times are rather large. But it was sufficient to say, the asteroid isn't quite where we were expecting it to be. And then we had two observations on October 18, Europe and Japan. And here, better prepared, better circumstances, got much better uncertainties involved with it. So tying down the position much better than that first one. And another two in October that year. And this one, first detection of Dimorphos. I think there was only two events where we picked up Dimorphos. A nice double event light curve there.
So Dave, just a comment. So the position of Dimorphos would be known from the mutual eclipses.
That's an interesting question.
No, I'm just wondering, because looking at that, you'd say, is there something there? But if we have the support that you know the position of Dimorphos from all the studies done, you'd be able to confirm that there's an actual detection.
Yeah. Yeah, there was they know what the orbit is around there. When it came to this, which was quite some time, that's more than 12 months after the actual impact, there was significant uncertainty about where it was in its orbit.
Okay, thanks.
But there was no doubt that was
the impact. That took quite a lot of studies, they would have known fairly accurately, but 12 months was enough to the brain, so you weren't quite sure if it was there or not.
Yes, there was quite an uncertainty. Sort of, they were expecting somewhere in that type of region.
Thanks. Really helpful.
Now, one of the interesting things I'll point out here, there's Dimorphos and there's Didymus. There's these groups of numbers in here. That's part of the occult reduction stuff. Now, I haven't properly done it on here, but for a centre of mass of a binary system, I can adjust the reporting system for the astrometry along there so that these numbers all become zero. And assuming uniform density, equal density of the two objects, that it becomes a reporting of the centre of the mass of the system. And of course, it's the centre of the mass of the system which you need for defining the gravitational motion around the sun. This one's an interesting one. You can see the observations don't fit the shape of Didymus very well. Issues of Fresnel diffraction were a major issue with the light curve interpretation, and that's an illustration there. Now, here's the one in 2004 and 5. That's the one in Melbourne. They had a whole heap of observers there. You should have got things, but the weather conditions, everything else, it was only the one observation. And there were questions about the time base for that, not serious questions, but some questions. This is John Broughton's. I've got the wrong annotation there. Really good results. John drove for 2 days to get out of the rain system into sort of Western Queensland, along a straight road in the middle of nowhere, and set up his various telescopes across there, and excellent results. Very well positioned body of Didymus. Problem is, when we did the analysis of that, this looked like there was really serious changes in the expected orbit. Serious in the sense of we can't figure out how to actually adjust the orbit to fit this observation. Then we had another observation a month later, and uncertainty is fairly large, but a reasonably independent observation. These two observers had completely independent systems, whereas this set of observations was actually made with local recordings at each station, but each one was set using a single iota VTI. So the time-based issues had a single source. And that's a significant issue for that. When that one was incorporated, there was an issue about how all these hung together and which ones are right, because you could not get a sensible orbit which matched all three. And I had a little bit of concern about this one, potential time-based issue, but nothing serious was there. And then John Broughton's one seemed to be serious questions about, was there something wrong with that observation? And you could do a fit to any two of these ones, which was a plausible fit. You couldn't do a fit to all three. What's going on? Fortunately, we had an observation in March this year in Japan. They had an excellent result there. And that fitted a good fit to that, and a reasonable fit to this one as well, and a misfit to this. Now, John went to a huge amount of effort to do this, and we went to a huge amount of effort to try to figure out what on earth is wrong with that. The star position was good. The observations are all consistent. Location is on a straight road in the middle of nowhere, a flat plain off to the side of the road, and you'd had to be 500 metres off the side of the road and setting up. There's just no doubt about his location. And then we wondered about his VTI and the process for synchronizing all his recording things. We went through all that process. Dave Herald and I forget the guy that actually designed the VTI. They had a look at all sorts of questions about the battery and backups and so forth. We could not find anything wrong with John's observation. It's inconsistent with everything else, and we have no idea why. But these observations all hung together and they become the critical things for what's been derived out of this set of observations. Now here's the best Didymus event, series of occultations around there. Here's Dimorphos, plotted in its physical location, and these are reported coordinate times. Even though these chords were missing the body, because it's a small body and the effects of Fresnel diffraction, they were all getting chords of some dip in the light curve caused by the presence of Dimorphos. When you've got a very small object and Fresnel diffraction's involved, you can get an occultation event even though the chord does not physically cross the asteroid's body. As we get to smaller and smaller asteroids, that's going to become a real issue. So, what is the astrometry you had to analyse all this data? Well, almost 6,000 ground-based array index, the type of thing that Alan Gilmore happily does or used to do day in, day out.
Well, nicely.
Yes. We have 22 occultation measurements, 3 optical navigation measurements from the DART spacecraft as it was approaching Didymus or Dimorphos, and 9 ground-based radar measurements. So that's the database used to analyse what's happened. So where do our occultation observations fit in this? Well, first of all, this is the set of astrometry being used, and here are the residuals of the final orbit fit. And you can see the residuals on RA and DEC, some scattered around, well, 2 milliarc seconds is a large residual, and I think most of it are down about 1 milliarc second. This is a weighted combined residual. I mean, there's a 1.8, but a whole heap less than a milliarc second. When you're doing ordinary CCD astrometry, you couldn't even dream of getting that type of precision. So how does it all compare? With all this data, they generate a series of orbits. And these orbits are looking at what's the uncertainty at the time of impact derived from the orbits. This blue ellipse is, where's the mouse gone to? This mouse likes getting lost. Mouse.
Up the other screen.
I need to look over here.
The right there.
Lives to the right.
No, it's over here.
Yes, and move to the right. It's on the other screen.
Oh, over
It's
here.
this screen, if you wouldn't have the wrong one, move the mouse to the right.
Okay. Oh, where's the mouse? All right. That blue ellipse is what the uncertainty was from just the optical observations prior to February 2021. Traditional astrometry, the scale in kilometres on the side and across the bottom. They undertook a detailed high precision ground-based astrometry leading up to the event. And when they did that, that's the resulting uncertainty ellipse, the best they could get from ground-based traditional CCD astrometry. And that's got an uncertainty of plus or minus 3 or 4 kilometres. Now, keep an eye on that ellipse. And that ellipse is this blue ellipse here. So increase the scale a bit. There's kilometres there. That ellipse there is when they incorporated the radar observations. Radar for close objects is pretty much the best ground-based way of getting astrometry from an asteroid. So that's what introduced with the radar. Now then they have the DART mission, the probe going in, and as it approaches Dimorphos, its optical navigation kicks in so it knows exactly where it's got to aim for, and they do the orbit adjustments. And somehow from that they can figure out, they must know where the spacecraft is in space with all their navigation stuff. When they introduce the operation, the onboard operational navigation system data, that's the uncertainty ellipse there. And that uncertainty is about half a kilometre. So now keep an eye on that ellipse. That ellipse there is the big blue ellipse. The first lot of asteroid occultation stuff gave this ellipse. That was the first 5 occultations. And then increased number of occultations to 14, reduced the uncertainty ellipse to that. And when 16 observations up till 23 January, so this is before the final set, it's the first set of observations. That's the uncertainty ellipse, and it's a 3 sigma uncertainty. And that's about 150 metres.
Yeah.
1 sigma uncertainty of 50 metres. Now compare that with traditional astrometry. It's this little dot in there. It's that blue, purple circle there compared to radar or the operational navigation system. Our astrometry that we can get is the best you can get from ground-based stuff. And this is by a bunch of amateurs with small aperture telescopes. You don't need $500 million to get that type of precision.
Yeah, Dave, the space telescopes, like a couple of generally years to Cook and observed at that time, will they be able to do better?
I doubt that they do better.
Because they've got limitations on how close they can point to the sun and that kind of stuff. So,
Yeah, and it's a matter of how accurately they know the spatial location of the telescope around the Earth at the time.
So it's doubtful if those space telescopes themselves will dominate.
I don't know.
Presumably it's such an important observation on that they could have asked for Hubble to be pointing to it.
Given the nature of that system, I'd be surprised. And of course, it's moving. The telescope itself is moving at a fairly large speed, so you've got to take that into account. Or it's there are no Hubble telescope observations of the system, and I assume for good reason.
Yeah.
I don't expect that they would.
Some observations of the original impact measured and checked and they have followed with the strong.
Yes. It's the astrometric acts you see. I mean, you can get pretty pictures of the ejector, but you just got to remember how many thousands of kilometres that long is, and you don't have the type of resolution. I mean, there's a resolution there down in milliarc seconds, and you don't do that. I don't think Hubble has that. Okay. So what has been learned out of the system? What's the results of our observations? Now, some before and after. The before columns of this is what they derived from the direct impacts from Dimorphos. And from the time differences when they did the observations of the change in the orbital period of Dimorphos around Didymus, this gives the before is what they derived. So they couldn't derive a change in the system velocity. They measured the change in the velocity of Dimorphos around Didymus, and it was a few millimeters per second. But what was the change in the heliocentric velocity of the whole system, which is what you really want to know for avoiding an impact? You could not determine that from looking at Dimorphos. From our occultation observations, and particularly those obtained last year and the one this year, that was measured, and I haven't put them up here because it's issued in publications, so I'm not going to have them on there. But the change in velocity was 11.7 plus or minus 1.3 micrometers per second. Now, doesn't sound much, micrometer per second, but if you've got a lot of seconds, it becomes a significant amount. But that is the first measurement obtained by amateurs with occultations of the deflection, a man-made deflection of an asteroid. I mentioned the issue of the projectile goes into the asteroid and you get the ejector coming out. In the initial impact analysis, they derived a value for this enhancement factor of somewhere between 2.2 and 4.9. And the critical thing here is they had to have a guess at what the massive Dimorphos was. The results that came out of the occultation analysis is that enhancement factor was 2.0 plus or minus 0.3. Previously 2.2 to 4.9. The mass of Dimorphos, they assumed a mass of about 2,200 kilogram, 2,000 a mass. They assumed a mass. I don't have the figure here. From the occultation observations, they derived a mass of 2.7 plus or minus 0.4 times 10 to the 9 kilograms. The density of Dimorphos, they assume 2,400 kilograms per cubic meter. The results from the occultation observations was 1,540 plus or minus 220 kilograms, kilograms per cubic meter, rather less than what they had assumed. Bulk density of Didymus, they didn't know. It's come out as 2,600 plus or minus 140. And they've got a mass ratio, they didn't know, mass ratio of 0.0051 to 1. Now, those values, much more certain than that. Really good uncertainties. And they're derived entirely from our occultations. Now that's a bunch of, and the paper which is being submitted to Nature Astronomy, Well, well, it's all done amateurs. It's better precision than you can get by any ground-based telescope. 20 to 35 centimetre apertures. And the acknowledgement at the end of a paper we've got submitted to Nature Astronomy, lists all the observers, and with the thing of worldwide collection of highly committed, not so amateur astronomers to going out into the middle of nowhere to observe this stuff. And not so amateur astronomers, I sort of like that. It's sort of not like amateur, they don't know what they're doing. And citizen scientists, well, we're not citizens as such, we're a bit more advanced than that.
Excellent.
And that's it. I mean, to me, what we've achieved with Didymus shows an extreme example of really high value observations which we can achieve, things which professional astronomers are unable to achieve, although professionals analyse it.
Yeah.
The final analysis of this is, don't know how they do it. So I'm open to questions.
We're a bit over 15 minutes at a time, so makes the questions quick, short, sharp. We've got
This
one.
may have a long answer. I'll do my best to make sure it doesn't. What was their plans if we weren't going to be there?
They just have to wait a few more years.
Right. Just long-term photometry and hope they can measure it.
Yeah.
Yeah. Okay. Thanks.
I mean, the displacement in the position
Yeah.
is several diameters,
Right.
but you're talking about several diameters, not millions of kilometres.
Yeah. So,
Do we have any questions online? I'm not looking at the chat.
While you're looking at it, just the comment, give an idea of what the densities mean. Water is density of 1,000 kilograms per cubic meter. So when you're talking about something that's 1 to 2 times more dense than water, which is typically rock. Rock is around about 2.
And
Yeah.
just picking up on that, one of the things that comes out of that quite different densities is that clearly the objects were separately formed. So they're probably come together rather than coming from the same mass.
Or they have differentiated and that we've got some frost off the top of Didymus and it coalesced into Dimorphos. That's for the theorists.
yeah.
That's all, but it's data which wasn't previously known in a serious way.
Just in case you thought you were wasting your time, you're really not.
Yeah.
No questions online? Nope. Good. We've done that, Dash. Michael?